So welcome to this next lecture. In previous lecture we have seen how to determine kinetics, of a gas liquid or a fluid reaction using model contactors. And in the previous lectures to that we had seen how to find out kinetics, different regimes, rate expression. We have solved some problems. Okay. Now in this lecture we are going to do design of reactors. Okay, so here let's get started. Just to get you to recollect all the things that we have done, we are on last part of our course, fluid reactions. We have done all these things: mass transfer with chemical reactions, model contactors. Now we are looking at design aspects of reactors. Okay, just couple of questions for you to revise so that you are better prepared for this lecture. Recall the rate expression for various regimes. Why should we use model contactors to determine kinetics of reaction? I'm asking why, not how. Okay, think about this. Give some examples along with sketches of model contactors. Describe a stepwise procedure that you will use to determine kinetics of a reaction for any one model contactor. Okay, here is a problem now. We are going to use all these information and solve a problem. So imagine that there is an impurity in the air that is to be reduced from 0.1% to 0.02% by physical absorption in water. This is like your undergraduate course, physical absorption, unit operations. Absorption is carried out counter current flow of air and water, 1 bar absolute pressure, 30 degrees centigrade. kGa you have been given. KLa you have been given. Henry's constant you have been given. Molar flux of air is given to you, 100 kilomoles per hour per meter square. Molar flux of water is given to you, 700 kilomole per hour per meter square of cross section. This is like mass flux or molar flux per unit cross section of the column. Recall your undergraduate lectures. If you don't recall, go and revise them. Coulson Richardson's book or McCabe Smith or Trebal, whatever book you have used, go and refer. This is physical absorption. You should be able to do this without even looking at this lecture. Okay. Pause and do it for yourself. Here's the solution. Okay, so G, molar flux of gas, 0.1% A. If total pressure is 1 bar, that means PA is 100 Pascal. Outlet we want 20 Pascal. Liquid, now there is no B here, it is physical absorption. So dissolved concentration of A in the inlet liquid is 0. Okay. QL, liquid flow rate, is 700 kilomoles per meter square per hour. Multiply that by 18, you will get kgs per meter square per hour. Divide by density of water, 1000, you will get 12.6 meter cube per hour per meter square. Okay. At any location, if I draw concentration profile, this is the gas side, this is your interface, this is liquid side. Gas side mass transfer film, gas side mass transfer resistance, liquid side mass transfer resistance. This is the concentration profile, undergraduate stuff. Write RA, right, in terms of mass transfer on gas side, right, RA in terms of mass transfer from liquid side. Eliminate PAI and A star by using Henry's constant, right? You should be able to get this. Now A naught at any location, this is our A naught, dissolved concentration of A in the liquid phase. Okay. And if I do differential material balance on this differential element, minus G into dYA would be RA into dZ. So minus G dy is d of PA by PT, total pressure, partial pressure of A divided by total pressure of A. Total pressure is constant. So RA. So RA now we can substitute from here. This is undergraduate stuff. RA we can substitute from here. To get to this A naught, we can do material balance across this whole cross section, across this whole part of the column, either the top part or the bottom part. What I have written is across the top part. G into YA minus YA out is how much A has disappeared from the gas side. That must be equal to QL into A that has appeared in the liquid side, minus 0, because A naught is 0 here at the start, at the entry top part. So we'll get A naught in terms of G and QL. A naught. Substitute that A naught here. You will get, and this. Okay, now all I have to do is integrate. Undergraduate stuff. This is how you are done. Height of transfer unit and number of transfer units. Remember? Okay, look at this. This is what? Sorry. This is, oops. This is the gas side resistance. This is liquid side resistance. You see, liquid side resistance is controlling. Simplify, integrate. You will get H as 504.6 meters, 505 meters. Just physical absorption. Undergraduate stuff. Okay. And then you can even define height of transfer unit, number of transfer units, and so on and so forth. Right? That's not important right now. Now, what can we do? How can we reduce this height? Think. How can we reduce this height? One option is allow reaction to take place in the liquid side. So if this pollutant is like H2S or carbon dioxide, have an amine in the liquid phase. They will react. Right? Let's assume right now that reaction is instantaneous. Reaction is instantaneous. So now all resistance is shifted to the gas side. There is no resistance on the liquid side. Right? Now calculate the height required. Do this for yourself. Pause the video and do it for yourself. Here's the solution. Same as like last time. PA is 100. Outlet we want 20. QL, B in, and now B out. B in, what is B in? 0.8 kilomoles per meter cube. That is told to us. Amine concentration. Now look at this expression. Look at this expression. This is how the concentration profile will look like. Reaction is instantaneous. Right? If reaction is instantaneous, look at what is the maximum possible A star. Maximum possible A star is 100 Pascal divided by Henry's constant. So A star is 0.008. Right? What is the unit of A star? What is the unit of Henry's constant? 12,500 meter cube Pascal kilomole. This is now 800.008 kilomoles per meter cube. dB B naught by Z dA A star. dB 1 B naught Z dA A star is 100. It's far greater than 1. That means even if at the bottom of the column, if gas side mass transfer was negligible, partial pressure at the interface would have been 100. The maximum possible value of A star anywhere in the column is this. Anywhere in the column A star is going to be lower than this. So anywhere in the column dB B naught by Z dA A star is going to be higher than this. Definitely lambda is tending to 0. Lambda is tending to 0. That means A star is 0. That means PAI is 0. That means reaction is completely controlled by the gas side mass transfer. Totally gas side mass transfer. Look at this. We had liquid side resistance and gas side resistance. Liquid side resistance was 40 times larger. 40 times larger. Now this resistance is going to be completely eliminated. It's going to be completely gas side controlled. So height is going to reduce dramatically. See? Okay, do this. G, overall material balance. Rate is now kGa into PA. Right? This 5.03. Just to make sure that B is not depleting. B is not depleting here. What do we do? G into Y in minus Y out would be equal to QL into B in minus B out. If you simplify, you will find that 0.8 is reducing to 0.794, practically no consumption of B. So it's okay to take B naught equal to 0.8 everywhere, and then this would be a correct estimate, right? So assume B naught is 0.8 everywhere throughout the column, because there is very little depletion of B, very little consumption of B. Stoichiometrically, B supplied is far greater than A consumed. Now H is 5.03, 100 times less. 100 times less. You see? That's how mass transfer helps us. That's the enhancement in mass transfer. Because of reaction. Enhancement in mass transfer. Because of reaction. Right? Liquid side resistance is eliminated completely. Here is another problem. It is desired to remove 90% of A present in the air by absorption in water. Okay. Another problem, similar problem. Okay. But now I'm going to give you rate constant. So A reacts with B irreversibly by second order rate law. Rate constant is this. Molar flow rate is 90 kilomole per hour. PA in is 1000 Pascal. Water flow rate is 16.2 meter cube per hour. Concentration of B at the inlet is 0.0556 kilomoles per meter. Mass transfer coefficient KLA, KGA given to you, A bar given to you, epsilon L, dB, dA given to you, Henry's constant given to you. Calculate the volume required. This is actually problem number 24.9 in Levenspil's book. Solve this yourself. Pause the video, solve it for yourself. Hint, if you want hints, draw schematic, do overall material balance, find out regime of operation at the top and bottom. Okay, do this, refer to these previous problems again and again, refer to the last two problems again and again, see how we have done, and do this. Don't go forward till you solve. Don't go forward till you solve. Solve on your own. Only when you solve things on your own, then things become very clear. Solve on your own. Here's the solution. So G now is 90 kilomoles per hour. PA in is 1000 Pascal. We want it to reduce to 100 Pascal. QL is 16.2 meter cube per hour. B in is 0.0556. B out. Let's do overall material balance and calculate B out. So G into Y in minus Y out would be QL into B in minus B out. So you'll find that B out is 0.0056. Right? So there is significant change of B naught with respect to height. B naught is reducing by a factor of 10. 0.0556 is becoming 0.0056. See? So I have to account for, we need to account for B naught variation with respect to height. Okay. Let's determine regime at the top of the column. Epsilon L K2 B naught 0.08 K2 B naught, right? 1.16 into 10 to 8 our inverse, because K2 is in our inverse. KLA is 72 our inverse. KLA is far less than epsilon L K2 B naught. What does it tell you? Definitely not in regime 1. To check whether it is 2, 3 or 4, calculate root m. Root m is dA K2 B naught by KL. dA K2 B naught by KL. KL is now, A bar is 100. So KL is 72 by 100. Root m is 100. So root m is greater than 3. That means definitely regime 3. At least. Maximum or minimum value of dB B naught by Z dA A star will be when A star is maximum. What is the maximum A star? PA by H. PA by H 10 raised to minus 6. So dB by B naught, dB B naught by Z dA A star is at least 55,600. Now you see 100 and 55,600. What does it tell you? That we are Root m is far far greater than 1, root m is far far less than dB B naught by ZdA star. So regime is 3 at the top of the column. So rate of reaction is root m into KL into A star, which is A bar A star root dA K2 B naught. This is the rate expression at the top of the column. Let's see what is at the bottom of the column. Again, epsilon L K2 B naught. Now B naught is different at the bottom of the column. Still, KL is far far less than epsilon L K2 B naught. Still, now root m has reduced because B naught has reduced. What is the maximum possible value of A star at the bottom of the column? It is PA by H. It is 10 raised to minus 5 kilomoles per meter. dB B naught by ZdA star is at least 560. So 31.8 is far far less than 560. So regime 3 even at the bottom of the column. That means if the reaction is in regime 3 at the top of the column, reaction is in regime 3 at the bottom of the column also. Right? Now look at this. Now look at this. This is now concentration profile. PA, there is mass transfer resistance on the gas side, dissolution, solubility, and there is constant. Now there is diffusion and reaction, and A naught is 0. Why? Because root m is far far greater than 1. And it is in regime 3. So A naught has to be 0. It is completely consumed in the film. So RA would be kGA at any location now, at any location. What we have to do? We have to look at any location, right? At any Z. We are taking differential element. At any location, RA is kGA PA minus PAI. RA is A bar A star root dA K2 B naught. Use Henry's constant. Eliminate the PAI. Okay. Simplify. This is now your gas side resistance, and this is now liquid side resistance, owing to enhancement in mass transfer. So RA at any location depends on B naught. How do you get B naught? Now you take material balance across the top of the column, across this red control volume, or you can take it across the blue control volume, this control volume. Either way you can get. You will be able to relate B naught to PA. Why? Because this we want in terms of PA. Okay. So if you take between top and any Z, G divided by PT into PA minus 100 would be equal to QL B in minus B naught at that Z location. Right. So we will express B naught at any Z location in terms of PA and the flow rates QG and QL. I have just simplified the values, but you can write in terms of QG. Now we can solve. Use this, solve this, and now you write material balance over this differential element dV, volume of differential element. And now if you simplify, you can do this integration on calculator, or you can integrate numerically in Excel. You will get 43 meter cube. Solve, do this for yourself. Do this for yourself. Make sure that you get the answer. Make sure you have understood everything properly. Understand all these concepts. How we are determining regime at the top, bottom. How we are determining regime at any location. How B naught is calculated at any location from material balance. How we are putting it in the rate expression. Right? Calculate for yourself. Calculate for yourself. Pause. Don't go forward unless you have understood this problem completely. The reason I am giving this problem solution in detail is because you should be able to understand and apply it to any other problem now. Okay, that's why I gave the answer in detail, and we discussed in detail. So solve for yourself. Understand all the steps involved. Come out with a standard calculation procedure if you like, based on these three problems that we have done so far. Let's go forward. Let's go forward. Here's the next problem. Terephthalic acid is produced by oxidation using oxygen from air of paraxylene in the liquid phase in a continuous steady state reactors. Reactor operates at 200 degrees centigrade and 20 bar absolute pressure. Paraxylene dissolved in acetic acid in the liquid phase along with dissolved homogeneous catalyst cobalt and magnesium acetate is fed to the reactor at a flow rate of 100 meter cube per hour. Paraxylene concentration in the feed is 1.9 kilomoles per meter cube. Assume that terephthalic acid is produced and water is formed in the reaction remains in the liquid phase. Assume that density of the liquid phase remains constant so that the liquid phase flow rate coming out of the reactor also is 100 meter cube per hour. It is desired to have 98% conversion of paraxylene. Oh, yeah. And 80% conversion of oxygen in the reactor. Intrinsic rate constant is 10 meter cube per kilomole second. Second order reaction. Assume that the diffusivity of dissolved oxygen and paraxylene in the liquid phase both are 1 into 10 raised to minus 9 meter square per second. Henry's constant for dissolution of oxygen in the liquid phase is 50 bar per meter cube per kilomole. Calculate the reactor volume required for three cases. 1. Stirred tank reactor, where both gas and liquid phases are well mixed. Now you see how the flow pattern is coming into picture. Spray column reactor, where gas is well mixed and liquid is plug flow. Bubble column, where gas is plug flow and liquid is well mixed. Now think about that first lecture where we had characterized the reactors. Now you see in the heterogeneous reaction, what do we need to know? How they are dispersed, co-current or counter-current, mixing, plug flow, well mixed, continuous, steady state, unsteady state, batch, plug flow, well mixed, adiabatic, isothermal. You see all those things. You go back to first lecture and see what are the characteristics required. All those things have to be specified now. Only then we can design a reactor. See, now the cycle is getting complete. We are completely back into the first lecture where we have to simplify and where we have to state all these characteristics. But now we are doing this for heterogeneous reaction. Reaction is between oxygen from air and paraxylene in the liquid phase. Solve for yourself. Try solving for yourself. You may struggle, it may take time, let it take time. Solve for yourself. Some hints if you want. Think about a generalized solution strategy from previous problems. Consider one reactor at a time. Let's say well mixed reactor, stirred tank. Draw schematic. Do overall material balance. Consider phase behavior. Write expression for RA. See how RA varies in the reactor. Integrate to calculate the volume. This is a reaction. Right? Z is 1/3 now. We have seen this earlier. Draw a schematic. Liquid is coming in 100 meter cube per hour. B in is 1.9 kilomole per meter cube. 98% conversion. So 100 meter cube per hour. B out is 0.038 kilomoles per meter cube. Air comes in. Air in, air out. Rate at which B reacts is 100 into 1.9 minus 0.038. 186.2 kilomoles per hour. Or 0.05172 kilomoles per second of B reacting. Rate at which A reacts is 3 times this number. This multiplied by 3. 80% of conversion of O2 is required. That means oxygen fed, 80% of the oxygen fed should be 0.15517. So oxygen fed to the reactor should be 0.19396. Nitrogen fed would be 79 by 21 into this. So this is just overall material balance. Okay. This you should be able to do. Any undergraduate student should be able to do. Undergraduate stuff, it is material balance. Okay. Now we can think in terms of solubility. Reactor is well mixed. So B0 in the reactor is 0.038. Everywhere it is well mixed. It is well mixed. Everywhere B0 is 0.038. You see? Gas is also well mixed. So everywhere A star is also constant. and A star would be PA by H. PA we should calculate at where? Well mixed equal to outlet. So PT multiplied by YA. So I need YA at the outlet. How do I get YA at the outlet? Nitrogen will remain as such. Oxygen, whatever comes in, 80% reacts, 20% remains. So then total divided oxygen moles divided by total moles will give you YA. So A star would be PTY by H, 0.0202 kilomoles per meter. Now you determine the regime of reaction. Now you stop and go forward. Now pause and go forward. See if you can go beyond this point and calculate the reactor volume. Here is the answer. Epsilon L K2 B naught. Epsilon L 0.8, 10 B naught. KLA, KLA. You see which one? Definitely mass transfer is limiting, but it could be react regime. Definitely not regime 1. It could be 2, 3, 4. Let's calculate root M. DAK2 B naught by KL. It's 0.195. Root M is far less than 1. So it is regime 2 operation. KLA is 10 times lower. Right? So RA is KLA into A star. Now write material balance for A. Minus G nitrogen into dy is equal to RA into V. Straightforward. Capital Y, you see kilomoles of oxygen per kilomoles of nitrogen. Y1 minus Y2 RA into V. So you solve this. This is nothing but kilomoles per second of oxygen reacting. Solve. RA is known. Volume would be 253.5 meter cube. So this is how, this is the dispersion volume. Dispersion volume. Okay. We have solved it for first case, A case. We have to solve for spray column and bubble column. Look at this procedure. Now you solve for bubble column. Now you solve for spray column on your own. Pause and solve on your own. Don't go forward. Here is the solution. Let's look at case B, spray column. Spray column means what? Air is coming in, air is going out. Liquid is sprayed at the top and liquid goes out. B in is the same, B out is the same, air in is the same, air out is the same, everything is the same. Material balance wise, overall material balance is the same, whether it is stirred tank or spray column or bubble column. Now, because liquid is in the plug flow, gas is in the well mixed condition. Now we take a small element dV and V plus dV. So B naught changes from top to bottom. Plug flow. As liquid drops travel, they react. B naught reduces. But gas is well mixed. A star is constant throughout the column, equal to the outlet condition. Now identify regime at the top and the bottom. At the top, if you do epsilon L K2 B naught, 1.9 second inverse. KLA 0.01 second inverse, root M 13.78, right? dB B naught by Z dA star 279, regime 3. At the bottom of the column, epsilon L K2 B naught 0.038, KLA 0.01, root M 1.95, dB B naught by Z dA star 5.59, between regime 3 and 4. See? For simplicity, let's assume that it is regime 3 throughout, just for our convenience. Okay. Here's the solution further. So now we do a differential balance. QL multiplied by dB naught would be RB into dV. RB would be Z times RA. RA is root M into KLA into A star. So Z times root M DAK2 B naught by KL square root KLA. KL will cancel out. Right. So QL divided by this, A star is constant, dV by root B naught. Now you integrate. Now this is to be integrated from inlet B in, so 1.9 to 0.038. That will be our volume. See, 96.7 meter cube. 96.7 meter cube. Although KL is lower. Look at this. Look at this. Oops. Look at this. We have done stirred tank, we have done spray column. Epsilon L is lower. KL is lower. Interfacial area is higher. But liquid phase is plug flow as compared to well mixed. This is the change. You see how things are different. That made that spray column volume reduce from 253 to 96. Now with these two things, spray column done, well mixed reactor done, now you do bubble column on your own. Stop the video, pause the video, do the calculations yourself. Only when you do, then only things will be clear to you. Do it for yourself. Here's the solution for bubble column. Overall material balance is still the same. Now, well mixed liquid, so B0 is constant throughout the column. A star changes from bottom to top. So now epsilon L K2 B0 is 0.3, KLA 0.03, root M 0.195. It is regime 2 throughout the column. Why? Because these things don't change. These things are not changing. Only A star is changing. So now G of nitrogen dy Ra dV, and dy would be y divided by 1 minus y, and you simplify further. Rate would be KLA into A star, regime 2. Now you simplify further. Pause and simplify further now on your own. Do on your own. Here's the solution. Right? You will get volume as 105 meter cube. Look at this. Look at this. What do we conclude now? Look at this. Now we are comparing situation A and C. Epsilon L is the same. KL is the same. A bar is the same. Only difference is gas is in plug flow as compared to well mixed. This is the only change. Regime also is the same. Regime 2 in stirred tank, regime 2 in bubble column, but regime 3 in spray column. Why? Because KL was lower. Only change is now plug flow versus well mixed. That allowed this volume to reduce from 253 to 105. See? Now what do you conclude? For the same reaction, regime will depend on contactor because KL will change. Okay. Plug flow, making the gas phase plug flow, changes the volume. KL is lower, but reaction is in regime 3. Higher interfacial area makes the required volume lower. Instead of 100, it is 1000, or 300, it is 1000. Okay. This is how we would design a reactor for fluid reactions. So some homework problems. Solve 11th Spiel chapter 424. Solve problems 24.5, 24.6, 24.8. Then compare with the answer of 24.9. Do these homework problems. Solve, only then you will be able to understand. Only then all these concepts will be reinforced and you will be comfortable with all these concepts. So we have come to the end of the course. Look at all the things that we have done from lecture 1. Real life reactors, adiabatic conditions, heat generation, RTD, gas solid reactions or fluid solid reactions, catalytic reactions, what kind of reactions happen, steps, adsorption, reaction, desorption, mass transfer, pore diffusion, fluid reactions, different regimes of operation. Understand all these concepts. You're going to need them, all of them, in your later on life, because all these are required for your practice. Most of the time it will be heterogeneous reactions. That's why most of the time we have spent on heterogeneous reactions. Nearly 50% of the course is on heterogeneous reactions. First 25% was on real life reactors, heat effects, RTD, very important. We have seen how making it well mixed to plug flow reduced the volume from 253 to 100. Everything else was the same, regime was the same. So understand all these things. If you don't understand, go over the lecture again and again and again. Read the book, read the reference that I have given to you at the end of the lecture. Then you will be able to understand. Okay. So let's stop here for our course.